I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will briefly discuss about an example problem for the type depth first search, that is DFS. This is one type of classification of uninformed search. Before going into the topic, let us discuss what type of data structure we are using in this depth first search. So in the previous lecture, we have discussed about BFS, that is breadth first search. In the breadth first search BFS, the primary data structure used is a queue. The queue allows BFS to explore all neighboring nodes at the current depth level before moving on to the nodes at the next depth level. This ensures that the algorithm explores the graph level by level. And whereas in the depth first search, the primary data structure used is a stack. This can either be explicit stack data structure or the call stack when using recursion. The stack helps keep track of the nodes to be explored and ensures that the algorithm explores as deeply as possible before backtracking. We'll see the algorithm. DFS algorithm steps first you should know. And the depth first search is an efficient algorithm for traversing or searching through graphs, right? So in this case, the depth first search is a graph traversal algorithm that explores the nodes by following one branch of graph as deeply as possible before backtracking. And what we'll do is starting from a root node, DFS explores each child node recursively or by using a stack. It continues visiting nodes along a single path until no further nodes are available. Then backtracks to the most recent nodes with unexplored neighbors to continue the search. This process repeats until all nodes are visited or the target node is found. DFS is particularly useful in problems such as pathfinding, puzzle solving, and cycle deduction in graphs. Its space complexity can be more efficient in certain cases as it only requires storing a single path in memory at any time. However, DFS can be less efficient than algorithms like breadth first search in some scenarios, particularly when the target node is near the root or in a shallow graph. So simple four steps. Starting at 0, push it into the stack and explore the first available neighbor, push it into the stack. Repeat until reaching a leaf node, then backtrack. Continue until all nodes are visited. So this is the example problem. The problem statement is perform depth first search DFS for this graph on the given graph, ensuring all nodes are visited. So first, the starting at what is the parent node here? This 0 is the starting node. That is, we have to start with the 0. We have to start with 0. This is the first step. In the first step, to start with 0. The algorithm begins by placing node 0 on the stack and visiting it. So the 0 is being put it into the stack and we are considering it as the visited this node. This is the starting point of the DFS algorithm. That is depth first search algorithm. This I'll show it to you on a table for this. So the first step, we are considering the starting at 0. The algorithm begins by placing 0, the node 0 on the stack. Here, we are given in the stack and visiting it. This current node. This is the starting point of the DFS algorithm. So the action for this is start at node 0. And the second step is from 0 to 1. Move to node 1. Node 1 is pushed onto the stack and the algorithm moves from node 0 to 1, exploring the next child. So here 1. So from this case, the current node is now move to 1, and next 1 comma 2, the stack from 1 to 2, but we have to traverse from here. So the in the stack 1 and 2 will be available. The third step is from 1 to 3, move to node 3. The algorithm moves deeper into the graph by visiting node 3, which is the next child of 1, and it onto the stack. Pushes onto the stack. Next step is the step 4. Move to node 6 from 3. From 3, the algorithm proceeds to node 6, adding it to the stack and continuing the exploration. And step 5 is move to node 6 from, that is 11 from 6. So this 11 is the leaf node. Once if it reaches the leaf node, the backtracking should be done. Node 11 is a leaf node, meaning what it says, it has no children. The algorithm moves to node 11 and records it as a leaf node. This we have to mark it in the graph. The action is the move to 11. This is the leaf node, and the current node is 11, and the stack 11 4 2 will be available. And next, after moving into the, that is 11, that is leaf node, here we have to backtrack. The backtracking should be done from 11 to 6. Backtrack to node 6. This is marked in the dotted lines. And 6 to backtracking to 6 to 3. That is 6 to 3. Since node 11 has no further children, the algorithm backtracks to node 6, then to node 3, and continues exploring other paths. And like this. So once if it reaches the node 1, it moves to node 4. After backtracking, the algorithm proceeds further exploration. Here we'll see the step 7. Node 4. So once if it reaches the node 4, move to node 7. It is the leaf node. The 11 is the leaf node. Node 7 is a leaf node, so the algorithm explores it and records it and moves back to node 4 after visiting, backtracking. And from node 4 to node 1. So from 1 to, that is backtrack to node 4 to 1 with no more children at 7. The algorithm backtracks to node 4 and then further backtrack to node 1 to continue the search. So next step is move to here, again backtracking, and then it has to move into node 2. Node 2. The algorithm moves to node 2, pushing it onto the stack and continuing the traversal. Next, from 2 to 5. From node 2, the algorithm moves to node 5, adding it onto the stack for further exploration. So the step 11 here, moves on to the node. This is the 11th step. At this time, in the values available in the stacks of 8, 9, and 10. And the 12th step is from 5. From 5, move to node 8. So here this 8 is the leaf node. Node 8 is a leaf node. So the algorithm visits it and then moves back to node 5, backtracking. From 5 to, it will go to 9. Move to node 9. So this is also a leaf node. Node 9 is also a leaf node. So the algorithm explores it and backtracks to node 5. Here backtracking. And then the last step is from 5 to, will go to 10. Move to node 10. This node is also a leaf node. Finally, the algorithm moves to node 10, a leaf node, and completes the traversal as there are no further nodes to visit. So one more time I'll explain. So this is the starting node. Here from starting node to 1, 1 to 3, and 3 to 6, 6 to 11. 11 is a leap node. It has to stop and have to backtrack from 11 to 6, 6 to 3, 3 to 1. Then we have another one more children for this one. So here, forward move 1 to 4 and 4 to 7. 7 is a leap node. It has to backtrack. Backtracking has been done and it has to go to 0. From 0 to 2, 2 to 5, from 5 to 8. 8 is a leaf node. Backtracking to be done and 5 to 9. Again, 9 is a leaf node and from 9 to 5, 5 to 10. So here the algorithm stops. So for this algorithm, this is the corresponding table. In this table consists of the steps to be followed. For this problem, there are 14 steps to be followed and stacks. There are values available in the stacks and the stacks to be filled from top to bottom, not bottom to top. From top to bottom, you have to enter the action to be done for each move. I hope this exploration, the final depth first searches 0, 1, 2, 0, 1, 3, 6, 11, 4, 7, 2, 5, 8, 9, 1. So 0, here, 0, 1, 3, 6, 11, then 4, 7, backtracking, 2, 5, 8, 9, 10. This is the output sequence. So coming into the conclusion, depth first search DFS is an efficient algorithm for traversing or searching through graphs, often employed in scenarios where exploring deep structure is essential. It starts at the given node and explores as far as possible along each branch before backtracking. This characteristics makes it ideal for problems like maze solving, the examples, and topological sorting and pathfinding. DFS is implemented using a stack. This I have said already. A stack data structure it is using either explicitly or via regression, which helps in tracking the nodes to be explored. So its time complexity is order of V plus E, where V is the number of vertices and E is the number of edges, making it highly efficient for sparse graphs. So I hope this explanation of depth first search, that is DFS, helped clarify its working and applications. DFS is a powerful and efficient algorithm for exploring deep structures in graph. By utilizing a stack, it ensures thorough exploration before backtracking. Hope all have enjoyed this lecture. Thank you.